First of all, just a note for this unit, because this unit is all math, you do need to show your work on each problem. So make sure you do that. Don't just write the answer, because then when I look at it, I will mark it wrong. Our first topic is on the mole. So just to give a little analogy of what a mole is, we're going to talk about a dozen. So it really doesn't have anything to do with chemistry, and I'm going to talk about some fruit, but it will be a good analogy to kind of introduce us to the concept of the mole. So first of all, let's say I have a dozen apples. What does a dozen mean? Well, a dozen means 12 of anything. So if I have a dozen apples, then I know that I have 12 apples. Well, let's, in the grocery store, go over to those hanging balances and take the weight. 12 apples, how much would that weigh? Just to keep it easy, we're just going to round up to 5 pounds. So we're going to say 12 apples equals 5 pounds of apples, which is a dozen apples. Let's apply it to another fruit, a dozen cantaloupes. Well, how many is that? I have 12 cantaloupes. And we can do the same thing. How much do 12 cantaloupes weigh? Each cantaloupe is usually around 3 pounds, so that's 36 pounds of cantaloupes. And let's apply it to one more fruit, a watermelon. If I have a dozen watermelon, how many watermelons is that? Well, there's 12, just like before, because that is what a dozen means. So it doesn't matter what I have. If I have a dozen, then that means 12. And watermelons can be 10 to 20 pounds. Let's just keep it nice and simple. Actually, those little tiny watermelons can even be smaller. But let's say we have each watermelon is 10 pounds, so 120 pounds of our watermelon. So I want you to notice that our fruits, I have the same counting numbers, 12 of each, and I can say I have a dozen, so it's like a group name, and I can also describe it by a weight. So notice our apples are a lot smaller than watermelons, so they're not going to weigh as much. So if I have a dozen apples, it's going to be 5 pounds versus a dozen watermelons would be 100. All right, so we can apply this concept of a dozen to this little conversion triangle here. So all of these three values are equal to each other. So a dozen is equal to 12 of anything, which is equal to a group weight. And so I can make this little triangle and I can compare them. So I can make what's called a conversion factor. And in a conversion factor, you're putting two things that are equal to each other on top of each other. So I can say that 1 dozen is equal to 12 of anything. And then I can flip it and I can say that 12 of anything is equal to 1 dozen. Well, what other values do I have there? I can say that my group weight is equal to 1 dozen, and I can flip it and I can say 1 dozen is equal to my group weight. And then I can say that 12 of anything is equal to that group weight. And I can flip it and I can say that group weight is equal to 12 of anything. So we are going to be using these conversion factors to change our units. And so we don't want to change the quantity of the thing that we're changing the unit for. We want that quantity to stay the same, but just call it by a different unit. And so I will multiply by a conversion factor. And it's like multiplying by 1, because if I have two things that are the same and I'm dividing them by each other, I'm going to get the number 1. All right, let's do a few math problems so you can kind of get used to these conversion factors. The first thing you're going to do is you're going to find the number that we need to convert. So in this first example, if you have 10 pounds of apples, how many dozen apples would you have? So I'm going to look for the number. So the number is right there. 10 pounds is where I'm starting. Okay, and I'm going to cancel out pounds. So I want pounds to be in the denominator or diagonal from the thing that I am canceling the units for. And what am I changing pounds into? I'm changing them into dozens. Well, from that previous slide, we know that for apples, 1 dozen apples equals 5 pounds is what we determined, okay? So we're going to include those numbers there. So We have 5 pounds here on the bottom and 1 dozen apples on the top. My pounds will cancel because I have 1 on top and 1 on the bottom, and my answer will be in dozen. And I tried to make the math easy. When you go across, then you are going to multiply. And when you cross that line going down, you're going to divide. So I will go 10 times 1 divided by 5, and I will get the number 2. We do need to double check sig figs. So whatever number you start with is how many sig figs you'll have in your answer. So remember, sig figs are significant digits. Remember, dot right, not left. So there's no dot here. So I'm going to start counting from the left, and I just count 1 digit. So this one only has 1 sig fig. And so I want to just make sure my answer has the same, and it does. So 1 sig fig. All right, let's do the second example. So on this one, I look for the number that I need to convert, and it's right there, 1.5 dozen apples. And I want to cancel out dozen, and so I'm going to put dozen here on the bottom, and I'm going to turn it into, it says how many pounds. So I'm going to turn it into pounds. So notice that this example is exactly the opposite of this conversion factor. So I'm just going to use the same conversion factor, but have pounds on the top, so 5 pounds, and 1 dozen on the bottom, okay? And again, these two things have to equal each other. Otherwise, it's not a conversion factor. So we are going to take 1.5 times 5 divided by 1. Dozens cancels. I'm left with pounds. And so 1.5 times 5 would be 7.5. Let's double check our sig figs. I have 2 significant figures there. And so I want to make sure that my answer also has 2, and it does. Okay, so let's apply what we've learned to chemistry. Can I have a dozen carbon atoms? You bet. A dozen carbon atoms would just be 12 carbon atoms. Is that a quantity that we can see? And the answer is no. We can't see a dozen atoms. They're just too small. So a dozen concept works great for donuts and for fruit, but it does not work for chemistry. So instead of using this number quantity of a dozen, we use in chemistry moles. So a mole is 6.02 times 10 to the 23rd of anything. And so what I mean by anything, I mean molecules, atoms, formula units if I have an ionic compound. So this anything could be molecules, atoms, formula units. It's whatever we need it to be in chemistry. And in chemistry, all these things are very, very, very tiny. But when I have this amount, this really, really, really large number, or a 1 mole quantity, I can hold that in my hand. So it's large enough that I can see it and I can work with it. And we're going to learn in our next goal topic molar mass. But this is kind of that weight quantity we use with the fruit. This is what we use for chemistry. We use a gram amount. And we find that gram amount by looking on the periodic table. And whatever the atomic weight is, or the atomic mass, we just put it in grams, and that will be equal to 1 mole. So we have, again, 3 quantities that are equal to each other. So I can take those 3 quantities that are equal to each other, and I can make a conversion triangle here where I can use any three of those values to convert my units. And just to mention, this very, very large number is called Avogadro's number. Avogadro didn't discover it or come up with it, but it was named in his honor. But again, we have 1 mole equals Avogadro's number of anything, and it's also equal to the molar mass in grams. And you find the molar mass in grams by looking at your periodic table. And if you look at whatever the element is, and there will be a number associated with it. And this right here, this is the molar mass. And every single element will have a different molar mass. And you just look at your periodic table. If you ever need grams, how many grams are in a mole? So you'll look up how many grams are in a mole for that certain element. Okay, so let's look at our atoms and some molecules. So look at some chemistry examples. So if I have Avogadro's number, or 6.02 times 10 to the 23rd of lead atoms, this is the quantity of 1 mole of lead. By the way, the abbreviation for mole is MOL, so I didn't forget the E. That's just this abbreviation. Doesn't abbreviate it very much, just dropping the E, but that is what it is, okay? And if I look on the periodic table, I find that on lead, 207 grams of lead is equal to 1 mole of lead. Now let's look at aluminum. Aluminum, I have 6.02 times 10 to the 23rd aluminum atoms. That is also equal to 1 mole, but of aluminum atoms. And looking on the periodic table, I find that it's 27.0 grams. It's okay to abbreviate the molar masses, but please don't drop it to 2 digits. We want to have at least 3, and 4 is even better. Let's look at the next one. I have 6.02 times 10 to the 23rd glucose molecules, or C6H12O6. So this is 1 mole of glucose. And when I have more than one atom, so here I have 6 carbons and 12 hydrogens and 6 oxygens, I'm going to add them all up from the periodic table. And we'll add up 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms, and I end up getting 180 grams. And I will talk more about those molar masses later. All right, so when we look at conversions, we can have conversion factors. And again, we have these 3 quantities that are all equal to each other. So I can just stack them on top of each other, just pick 2 and stack them on top of each other. So 1 mole is equal to Avogadro's number. And again, this is of anything. So it can be atoms or particles, or it can be molecules, just whatever I need it to be in chemistry. So typically in chemistry, they're really, really small things. So that's why this number has to be so big. So I have those 2 conversion factors. I can also say that 1 mole is equal to the molar mass. So remember, you get that from the periodic table in grams. And then I can flip-flop it. So I can say the molar mass on top is equal to 1 mole. And then we can also compare our, what do we have left? We have molar mass and Avogadro's number. The 6.02 times 10 to the 23rd of anything. And again, which one we use just depends on what conversions we're trying to do. Okay, Avogadro's number on top, and then molar mass. And again, I get that from the periodic table. All right, so there are my 6 conversion factors. And again, whatever you're trying to convert, you will just try to match it up so that that unit that you're trying to cancel out will be at the bottom. Then notice that they're all the same. So whatever's on the top and whatever's on the bottom, they are equal to each other. That's what a conversion factor is. All right, let's do some examples here. So sometimes there's a big, long story problem, but on this one, I tried to make it nice and simple. So you're given the quantity here, and then you have to change it to a different unit. So write whatever number they give to you first. So I have this many carbon atoms, and I want to cancel out atoms. So atoms goes down here at the bottom, and moles goes here at the top. And I don't have my little conversion triangle on this slide, so I can just draw it really quick. Make sure that you use this until you get used to these, so you can refer to this conversion triangle. So whenever we make conversions, it will be one of these. All right, so we have Avogadro's number equal to moles equal to the molar mass, which I get, again, from the periodic table. All right, so I have atoms. I need to change to moles. So looking on that conversion triangle, I'm right here at this, between these 2. And I'm going to write my atoms down here at the bottom, because atoms are not moles and atoms are not grams. So it has to be Avogadro's number. So that's 6.02 times 10 to the 23rd anything. In this case, instead of anything, it's atoms. And at the top, I have 1. So I tried to make the math easy. So we multiply and then divide. If you notice the 3.01 and the 6.02, the 3.01 is exactly half. So my answer here is 0.5 moles, because atoms cancel. And I just need to double check my sig figs. I'm starting with 3 sig figs, so I want to make sure I end with 3. So whatever number you start with, you don't look at your conversion factors for your sig figs. So even though there's a 1 mole right there, I don't have 1 sig fig because it's actually 1.000000 moles, how many I need. So always start with whatever you start with as far as significant figures is what you're going to end with. So this is how many moles of carbon I have for this problem. Let's do the next one. So now I have 3 moles of carbon, and they want how many grams. So I'm going to put moles on the bottom, and then I'm going to change it to grams. And looking at my conversion triangle, I am going to be between moles and grams, so right here, okay? So using those two. So at the bottom, I'm going to have moles, and I know that I have 1 mole is equal to the molar mass in grams, and I look on the periodic table for this. So I don't just pull this out of thin air. I actually look at where carbon is, and carbon is 12.0 grams, and that's just with 3 sig figs. It lists a little bit more on the periodic table, but remember, I always want you to use 3, if not 4 sig figs. So we go ahead and multiply and divide. I have 3 times 12 divided by 1, so I get 36 grams. Let's just double check our sig figs. I start with 3 sig figs, so I want my answer to have 3 sig figs. So 36.0 grams of carbon, okay? Let's do one more example here. Let's do one more example. So on this one, I'm starting with 36 grams of carbon. I want to cancel out grams, and I want to change it to atoms. So looking at this, I know that I'm in grams, and atoms is not moles, so it's not that one, it's Avogadro's number. So I'm using these 2 bottom amounts. So I have 12.0 grams, again, I get that from the periodic table, is equal to 6.02 times 10 to the 23 atoms. So on this one, I will multiply 36 times 6.02 times 10 to the 23. Make sure you use your exponent button on your calculator for these large numbers. So press your EE button, or sometimes it's your EXP button, and then 23. Don't use your caret button, so your calculator sometimes gets confused. So multiply these 2 numbers, and then I will divide by 12. So when I do this, I get, if I kind of do this in my head, I get 18 times 10 to the 23, and then move me my decimal over, I get 10 to the 24 atoms. Let's just double check sig figs. I have 2 sig figs, and I also have 2 there. So there's my answer. So again, you use whatever conversion factors that you need, and they will always be equal to each other. So this value is equal to that. They're both equal to 1 mole. One mistake I see students make is they try to tell me that they have 1 mole is equal to 1 gram of something. And this is not correct. For hydrogen, maybe, because hydrogen is our only element that has a molar mass of 1. So we would only see that with this. So these two typically are not equal to each other. You're going to have a number much bigger than 1 for 1 gram. So it's usually 1 mole, but not 1 gram, unless it's hydrogen. All right, so I want you to stop the tape and go through these and do your conversions for 1 and 2, and then we'll go over the answers. Okay, we're back. So at the very, very top, we have 1 mole of water molecules is equal to 18 grams. I get that from my periodic table. And looking up oxygen, oxygen is 16. And each hydrogen is a 1, and I have 2 of them. So when I add all those up, I get 18. So that's where I got that. And it's also equal to Avogadro's number. Remember, Avogadro's number is equal to a mole. And this time it's molecules that I'm going to have as my unit there. So your answer to number 1 is 3.3. And your answer to number 2 is 2.0 times 10 to the 24th. Okay. So looking at this, you're going to start with the 6 grams or the 60 grams. You're going to cancel out grams by putting grams down below. And we're going to have On the top, we're changing it to moles. So 1 mole on the top, and looking on my periodic table, and I've already done that, 18 grams here on the bottom. So when you divide this out, you get 3.3 moles. And let's look at this next one. So it doesn't matter if you start with the 3.3 or the 60 grams because you're going to get the same answer. But let's say we go ahead and start with the 60 grams. And so we're going to put those 18 grams at the bottom. And this time we're going to change it to molecules. So I'll put my molecules there at the top. And write out the word molecules because if you abbreviate MOL, you might get confused for moles. So when you multiply this all out, you do get that 2.0 number. Okay. The mole song, I will put a link on to a YouTube video so you can see that. All right, so let's do the topic formula or molar mass. Both of these mean the same thing. Sometimes it might be called molecular mass. And this is when you look on the periodic table and look at those atomic weights or those atomic masses, and you just put the unit G for grams at the end, okay? And this will be your molar mass, or the amount in 1 mole. How they got these numbers is before like 1960-ish, they used to compare both hydrogen and oxygen, or all the other elements were compared to hydrogen and oxygen. After about 1960, they decided to use carbon as their comparison. So this might be one reason why hydrogen, oxygen, and carbon are pretty close to a whole number as far as their molar mass, okay? So the formula mass, typically we call it a formula mass if I have a formula. So this would be like an ionic compound like sodium chloride, or it could be something like, oh, I don't know, ammonium nitrate. There's 2 polyatomic ions put together. These are salts or ionic compounds. So because there are these huge crystals, we look at the lowest ratio and we call that the formula, the ionic formula. And so these are called formula masses. So we just add up the lowest ratio. So the units are grams per mole. You also can see them as atomic mass units. So, but really it just means the same thing, okay? So we have grams per mole. These are our molar masses. And again, you're going to use the periodic table. So this says, what is the formula mass or the molar mass of aluminum? And again, when you write that down, I want at least 3 sig figs, if not 4. So 27.0 grams per mole. All right, so let's practice. We're going to calculate the formula mass in grams of each of the following. So looking here, we have calcium. And again, I'm going to look at the periodic table. So I'm just not pulling these numbers from the air. I'm actually looking these up. So if you look at calcium, if we round to 3 sig figs, we get 40.1 grams per mole. And oxygen, looking that up, is 16. And I just add them up. So I have 56.1 grams per mole. All right, let's look at O2. So this is oxygen, but I have 2 of them. So I can multiply my 16 that I look at my periodic table by 2, or I can do 16 plus 16. Either way, I'm going to get the answer 32 grams per mole. And let's look at this next one. So we have aluminum is the 27.0, and chlorine, I have 3 of them, and I'm going to multiply 35.4 and multiply it by 3. And that is 106.2. And then I'll add that up to the 27, and I get a total of 133.2 grams per mole. All right, let's do one that has parentheses because that's about the hardest thing I can throw at you. And let's just do this middle one. So we have calcium right here. Calcium, I have 3 times the 40.1. And for the phosphorus, you're going to take that 2 and distribute. So I end up having 2 of these phosphorus atoms. And so I'm going to round that to 31.0. Okay. So doubling that is 62. And if you look at the oxygen, you multiply. So 2 times 4, I have 8 oxygens. And we'll just add all those up. And I get a 310.3 grams per mole. So again, I use my periodic table and you just add them up. So if you don't want to multiply, for example, the calcium by 3, you could put in your calculator 40.1 plus 40.1 plus 40.1. So you're going to get the same answer.